And of course, so this is characteristic of the material, and these numbers are important, so people measure these numbers. Okay, and here's it's called the coefficient of linear expansion. Okay, and here are some numbers. For aluminum, the number is 25 times 10 to the minus 6 per degree Celsius. Okay, let's see what this number means. Okay, if this is 1 meter, the increase, and you raise the temperature by 1 degree Celsius, then the increase in length will be for aluminum 25 times 10 to the minus 6 meters. Okay, 25 parts in a million. Okay, a thousandth is a millimeter. Okay, 0.025 millimeters is what it would expand. So that's what this number is telling you. So you take a 1 meter aluminum rod, you raise its temperature by 1 degree Celsius, its length increased by 0.025 millimeter. Again, the length increased by 25 parts in a million. Why the heck are we talking about this? Why do we care? All right, so here's a bridge in Michigan. It's about a kilometer long. Kilometer is from here to Embry-Riddle campus. So that's how big the bridge is. And between winter and summer, it sees 100 degrees Celsius change. The length of the bridge would increase by 1.5 meters. 1.5 meters is as tall as me. You have to account for that. You got to accommodate for that. Okay. How do we accommodate for that? See, we leave gaps between spans. Okay, so this is how the span gap looks like in the winter. And so now during the summer when it heats up, you want this have enough room for its expansion. What happens if there's not enough room for expansion? This happens. Okay. So the forces would be so large that the spans would push against each other and crumble. Yeah. Yep.
Do you know how much space you're supposed to have between each of the finger sets?
Mm-hmm.
Does it just depend on the length of it and how much space you need?
Yes, I mean,
Okay.
so that as an engineer you would calculate that. Yeah.
Okay.
Mm-hmm. Okay, and so this table will be your friend. Okay. Yeah. You calculate and you see the worst temperature changes you can see. Calculate the expansion. If it's 3 millimeters, what do? You leave a gap of 5 millimeters. Yep.
How do you account for the difference in concrete?
Yes, so you calculate the weighted average alpha.
So how do you keep the roads on a bridge from cracking compared to the aluminum? Do you do segments?
Say that again.
How would the concrete not crack on the bridge if aluminum
Mm.
and asphalt would expand?
Well, I mean, cracking does happen in the winter. You see that all sidewalks crack and stuff like that, but that's a materials property. Yeah. Mm. So anyway, so you have to have expansion gaps. Okay. And here's another application of it. So you can make thermostats. Okay. So for instance, okay, so here's an electrical contact in the room. You have a heater on, and when it gets too warm, you want to shut off the heater. When it gets too warm, see, this is made of two different metals. When it gets too warm, it bends upward, and the electrical contact is lost, and it shuts off. When the temperature falls again, it'll bend back, and the heater will go back on. So, by the way, the Trans-Siberian line is 10,000 kilometers, which is twice the distance from New York to San Francisco. And it sees a temperature change of 70 degrees Celsius, and the length changes by 8 kilometers. So all those gaps add up to 8 kilometers. 8 kilometers is from here to State Road 40 to Ormond Beach. Okay? You can do the following. Okay, so here's an interesting fact. So let's say this is an aluminum washer. You heat this washer. The question is, how does this gap expand? Okay. It turns out that this gap expands exactly as if it was the material outside. So if this was an aluminum washer, this gap would expand as if it was aluminum. If this was a steel washer, the gap would expand as if it was steel. Okay. And to see that, just imagine this guy. You heat this, the whole thing would expand like that. And you know, that ring is expanding like whatever material it is. And so if you remove the ring, the gap would expand exactly the same way. So here is a connection you can make. So for instance, if you want to make a ball socket joint, and obviously you want to make the ball bigger than the socket. So how do you install it? You heat the socket, make it expand, and then insert the ball, and then once it cools down, you have a ball socket joint. Yeah. This is used in airframe manufacturing as well. Airframes are aluminum. Try and use an aluminum screw. The threads would wear off. So how do you make a good connection? You take aluminum screws, dip them in liquid nitrogen. They'll become smaller, insert them, and then when they warm up, they'll be a good bond. Okay. How does the area increase? How does the area increase? The increase in area of any material is twice alpha, coefficient of linear expansion, times the area of the object times the rise in temperature. Similarly, volumes also expand as the surrounding material. The volume expansion coefficient, beta, is 3 times alpha. So the increase in volume of a solid object is beta times initial volume times the rise in temperature. So here's an interesting graph. Okay, what is the density of a material? Rho is mass times volume. Okay. What happens to the volume of a substance as you increase its temperature? As you heat something up, what happens to the volume?
Goes up.
It goes up. And so you can see the density should go down. Okay. So as the temperature rises, the density should go down. As the temperature rises, so this is for water. As the temperature is rising here in this window, look at this, the density is going up. Very unusual. And it's very unique as well. So, and only in this small window. After that, for these temperature range, it's behaving normally. The density is going up. And this is not a very big effect, so this is about 10 parts in 100,000. Very small effect. But this got very important consequences, so this part of the graph. So let me tell you about it. It's important for life. Do you guys know how to freeze a lake? How do you freeze a lake? You've never frozen a lake? What kind of an engineer are you? How do you freeze a lake? All right, you go home, flip the switch, and make the air temperature minus 20 degrees Celsius. Okay, so here was a lake at 10 degrees Celsius. And what will happen now? Heat will flow from here to there. Okay, so eventually, let's say this gets to 4 degrees Celsius. Okay, and well, so this was losing heat faster, and this is at 10 degrees Celsius. And you saw the graphs. At 4 degrees Celsius, the density is highest. So this water will sink to the bottom. This will get to be 4 degrees. Eventually, all of it gets to 4 degrees Celsius. And you're still losing heat. So all of this water is at 4 degrees Celsius. This loses heat, it gets to 2 degrees Celsius. But now this is less dense than that. So this doesn't sink. If it was some other liquid, that would have sunk. If it was alcohol, that would have sunk. But this is water. It remains there. This loses further heat. It eventually freezes. And that's another property of water. Ice is less dense than water. Yes, so now you've frozen the top part. Now an ice is a good insulator. Now you have cut down the flow of heat. So you try and freeze a lake, all you end up doing is you freeze the top part. And this guy doesn't freeze. So you're a failed engineer, and this fish is happy for it. So that fish can live through the winter. Okay, so you see that curve is very important for life to have survived the winters. All right, so what is heat? Heat is, a solid, these atoms are vibrating, and there's potential energy in the springs and so on. Okay, so, and as this guy is vibrating, the length of this guy is changing, so the potential energy is random as well. Okay, heat is the sum of this random kinetic and potential energy. Okay, that's the internal energy, and when you exchange this internal energy, that is heat. Okay, so when two objects, when heat flows from this object to that object, from A to B, then it's that random internal kinetic and potential energy that is moving. Okay? So when heat flows from here, these vibrations of these atoms are getting smaller, and vibrations of these atoms are getting larger. Okay? So internal or thermal energy of a system is the random internal kinetic and potential energies of the microscopic constituents of the system. Okay, so let's say I have this object. It is at a certain temperature, 22 degrees Celsius. Did that raise its temperature? Did this motion raise its temperature? No, temperature is a measure of the random internal kinetic energies. Yep. So it's not dependent on this overall kinetic energy. Okay. So back in the old days, 200 years ago, 250 years ago, something like that, they didn't know that heat was this random internal kinetic and potential energy. They thought heat was some kind of fluid. Okay. Once they realized heat was a form of energy, okay, so they knew the unit of joule, which was the energy, the potential energy of this guy, the kinetic energy of that guy. They knew that. Once they realized that heat was a form of energy, they had to find this conversion from calories to joules. And a calorie is defined as, 1 calorie is defined as the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay. And 1 gram of water is, can you hold your bottle? It's about a capful. Okay, so to raise the temperature of a capful of water by 1 degree Celsius, you need 1 calorie of heat. Okay. And by the way, you should be aware of, so that's 1 calorie. And a food calorie is a big C, which is 1,000 little calories. Okay? So you really eat 2.5 million calories. Okay? But we don't want to scare off people, so we call it 2,500 calories. Yeah. All right, so how was this found? Mr. Joule found it, and that's why we named this um, the Joule, energy of Joule. Okay, so you have this paddle, and what you do is you hang a weight, and as the weight falls, the amount of energy, potential energy lost by this weight is mgh, and you could calculate that in joules. And as this is falling, and as it's falling at constant speed, it's losing potential energy, and that potential energy is being turned into heat here. The paddle is warming this water. You can measure the rise in temperature, and you can calculate the amount of heat, and this can be calculated in calories. Okay? And so this many joules got converted to that many calories. By the way, this is the mass of water, and this is the mass of the weight. So, okay. So, and 1 calorie is 4.184 joules, or 186, something like that. Okay, we define specific heats for solids and liquids. Okay. Solids and liquids, the easiest way to measure how much stuff you have is by how much mass, by measuring the mass, okay, for solids and liquids. What is the most convenient way to measure how much gas you have? I'm sorry? How many moles of gas you have, okay? So when you're talking about gases, you say how many moles you have. When you are talking about solids and liquids, you say how many kgs of solid or liquid you have, okay? So for solids and liquids, we define something called a specific heat, and here's the formula. Okay, Q is mc times delta T. So what this formula tells you is, if you have m kgs of a solid or liquid, and you want to raise its temperature by that much, this is the amount of heat you need. And this is the specific heat of the material. So what that tells you is the amount of heat needed to raise the temperature 1 kg of stuff by 1 degree Celsius. Okay, so that's what the specific heat tells you. The specific heat tells you how much heat do you need to raise the temperature by 1 kg of material by 1 degree Celsius. Okay? And again, that's a characteristic of the material. Okay, so but when we come to gases, you don't measure the amount of stuff in mass, you measure it in number of moles. So we'll call molar specific heat when we come to gases, but we'll come to that next chapter. Look at this, here are the specific heat. Again, these numbers are important, so whenever something is important, whenever you see a table for something, that means that number is important and is useful. Okay? And somebody's gone to the trouble of measuring stuff. Okay? Look at this, the specific heat of water is 4,200 joules per kg per degree Kelvin. So 1 kg, that much water is 1 kg of water. No, that's half a kg of water. So take 2 bottles of that, and to raise the temperature by 1 degree Celsius, you need 4,200 joules of heat. Look at this, silicon. Okay, you pick up a handful of dirt, and that's essentially silicon dioxide. Its specific heat is 700, 6 times less. So it's much easier to warm ground, soil. All right, let's do the following now. Okay. So what we do is, okay, so if the specific heat is lower, you have the same amount of heat falling, the specific heat is lower, the temperature will rise more. Okay? So, let's say this is land, water. Okay, so let's say we have equal amounts of radiation falling during the day. Okay, so equal in 1 hour, so much heat fell in the form of radiation. Okay. Q, this much heat fell. This is the specific heat. Okay, remember the specific heat of water is 6 times greater, so the temperature rise was 6 times less. During the day, the water warms up less, the land warms up more. So the temperature of land is risen higher. This air warms up greater than this air. This air gets less dense and it rises. So during the day, you have a low pressure here, you have a higher pressure here, you get a breeze like that. Okay? So during the day, you get a breeze from the land to water. Well, at night, what happens? Well, this guy rose to a higher temperature, but he didn't have as much heat content, and he cools faster at night. This guy has a lot of heat content, so he doesn't cool as fast. Okay. So at night, this is warmer, this air rises, and you get a breeze like that. So if you have waterfront property, not only is it pretty, you get a breeze all the time. During the day, you get a breeze from the water, and at night from like that. That's why this property is expensive. Okay. So you came for a physics class, and you're getting a real estate class. All right, so you see that number is extremely important. The specific heat of water is very high. Okay. Now we'll talk about latent heat. Okay, here's a can of water, and if I put it on the range, what will happen?
Start to boil.
Its temperature will rise. Okay. Now let me give you a bunch of ice cubes at 0 degrees Celsius. The ice cubes that come out of your freezer are at -5 degrees Celsius, but we'll say it's at 0 degrees Celsius. I'll put that on the range. What happens?
Does it heat up faster?
Okay, so the temperature will not rise. You have it on the range and the temperature is not rising. Where the heck is all the heat going? The heat is going into melting the ice. And the temperature of this won't rise till all the ice is melted. So all that energy, where it went into breaking these bonds. Okay, and that is called latent heat. The heat that does not raise the temperature of an object is called latent heat. Okay, and that happens during phase change. Okay, so it'll happen from the phase change from solid to liquid. It doesn't happen for all substances, but when it happens, that is called latent heat. Okay? And that's to break the intermolecular bonds and stuff like that. So it turns out to melt 1 gram of ice, water ice, you need 80 calories per gram. Okay. So to melt 1 gram of ice, you need 80 calories of heat. And that heat does not raise the temperature. Okay? So when will the temperature rise? All of the ice has to melt. Okay? And so the job of the heat is to first melt all of the ice, and then the temperature will start rising. Okay? So that's what this graph is showing you. See the temperature versus the heat added. So if you take ice at, let's say, minus 20 degrees Celsius, you can warm up the ice. Once the ice gets to 0 degrees Celsius, now all of the heat is going into melting the ice, and you see the temperature is not rising. When all of the ice melts, now you can warm the water to 100 degrees Celsius. Okay. Once the water warms to 100 degrees Celsius, now you can't raise the temperature of the water. This is all at 1 atmosphere. All of the heat is going into vaporizing the water to steam. Once all of the water has become steam, then you can raise the temperature of the steam. How far can you go raise the temperature of the steam? As far as you want. Once, if after it starts ionizing and stuff like that, then it's no longer steam. Anyway, all right. So during phase change, the heat added is the mass converted from one phase to another times the latent heat. Okay. So this is the formula when the temperature is not changing. So that's latent heat. Okay. Okay. The latent heat for water is a very large number. So this is latent heat of fusion, and this is latent heat of vaporization. Latent heat of fusion is when you're going from solid to liquid, and heat of vaporization is when you're going from liquid to gas. These are numbers in joules per kg. This number is easier to remember, 80 calories per gram, and this is 540 calories per gram. Okay. Now we'll talk about this. What this number says is to vaporize 1 gram of water, to convert 1 gram of water to steam, you need 540 calories of heat. Okay. So if you want to convert 1 capful of that water into steam, you need 540 calories of heat. To heat that 1 gram of water from 0 to 100 degrees Celsius, all you need is 100 calories. You need an enormous amount of heat to convert it into steam. Okay. So, and biology uses all these numbers. Systems use all these numbers. So here's an amazing number. Okay. So I'm going to speed up, but if it's interesting, then I will be slow. Okay. So let's say we're cooking potatoes. We're boiling water. Water is boiling at 100 degrees Celsius. And this is taking 30 minutes to cook. Now you don't have the patience. You want to cook faster. Is there anything you can do? Yeah. If this cooked at 110 degrees Celsius, it would cook in 15 minutes. But how do you make water boil at 110 degrees Celsius? If it cooked at 120 degrees Celsius, it would cook in, let's do 40, 20, 10 minutes. So every 10-degree rise in temperature, the reaction rates are doubling. So if you could cook it at 120 degrees Celsius, you could cook it faster. You'd save energy. That's what a pressure cooker does. Water boils at 100 degrees Celsius at 1 atmosphere. At 2 atmospheres, it'll boil at 120 degrees Celsius. So you build up pressure to 2 atmospheres in a pressure cooker, and the water is boiling at 120 degrees Celsius, and stuff is cooking faster. You're a thermodynamic system, but you are a machine, very precise machine. There's thousands of reactions going on in your body. They're all interdependent. You cannot just raise the reaction rates. You raise your body temperature, all those reaction rates would go higher, and that balance would go out of whack. And you won't feel good. You all know that. What's your body temperature?
98.6
Yeah.
degrees.
roughly 100 degrees, 98.6 degrees, and you raise his body temperature to 99 degrees Celsius, Fahrenheit. You change it by 1 degree and he starts crying.
Just one time.
Huh?
Just one time.
One. Right? You don't like your body temperature being changed by 1%. Okay? That's because all the reaction rates have increased and that you've thrown the system out of balance. All right, look at this. So, you guys understand this problem? So, to maintain your body, so he's a 100-watt bulb. So, to maintain this thermodynamic system, you're producing 100 joules of heat per second. So now if you don't want to raise the temperature of this thermodynamic system, I'm getting rid of 100 joules of heat per second. Okay? Now let's say I go for a run. Now I'm producing 1500 joules per second. So suddenly, just like that, my air conditioning system has to work 15 times harder. Because I don't want to raise my temperature. So how do we do that? So we take advantage of this number. Yeah. So what you do is, when you go for a run, you sweat. And that doesn't do it. When sweat evaporates, every gram of sweat evaporating takes away 540 calories of heat. That's how you cool. So when you develop sweat glands, that's when you could start running. Okay? So that's your cooling system. Okay, so we take advantage of that. So what if it's 100% humid? If the humidity is 100%, you don't want to go for a run because your sweat won't evaporate. You don't want to put a treadmill in a sauna. Your cooling system won't work. So when sweat evaporates removes heat from your body. Okay? So our cooling system is extremely efficient. It's claimed that people have survived temperatures long enough to cook a steak. So apparently, here's a steak and a person in an oven, which is at 260 degrees Fahrenheit. And the steak cooked and this guy walked out. Okay, I'm going to speed up a little. Okay, so Lake Superior is roughly half the size of Florida. Okay, so here's one of the big lakes. So here's the lake. The next few slides just show you that the enormous amount of energy that nature moves. Okay. So here's lake. During the winter, as much as 150 centimeter thick layer of ice can form on the lake surface. So you can draw better Florida. Here. It's a boomerang, but you want to cover half of Florida with this much ice. Okay, 1.5 meters, 150 centimeters. Okay, what do you have to do to make ice from water? You have to, I'm sorry? You have to remove an enormous amount of heat. Remember, to make 1 gram of ice, you have to remove 80 calories of heat. Okay. To form a 156 centimeter layer of ice on Lake Superior, as much heat as contained in 10 million atom bombs must be removed. To form that layer of ice, you had to remove heat of 10 million atom bombs. And then what do you do in the summer? You put it right back. Okay? And that's just one piddly little lake. Okay? So, so when you have two objects at different temperatures, what happens? Heat flows from the hotter object to the colder object. Okay? So hot, cold, heat will flow from here to there. And there's three mechanisms by which heat can flow: conduction, convection, and radiation. Okay? So here, this fellow is getting heat via conduction. This person is getting heat via convection. Okay, convection is this air is warmed up and it gets less dense, it rises up, and the warm air transfers heat in. So that's convective heat transfer. And there's radiative heat transfer. Okay. All right, so so I mean, it's summer, and if we didn't keep the temperature to 22 degrees Celsius inside this room, you would not come to this class. The outside temperature is about 35 degrees Celsius, and so heat is flowing in from the outside to here. Okay? And then we are having to take this heat away continuously, and it's costing us money. Okay? This tells you conductive heat flow. Amount of heat flowing in this time that depends on the thermal conductivity. So heat flows from a hotter region to a colder region. It depends on the thermal conductivity of the material. Okay, so more heat flows in, more money it's costing you. So what you want to do is make this number as small as possible. So what do you do to make that number? You stuff it with insulating materials, the walls with insulating material. This guy, that's expensive, that window. That guy lets in a lot of heat. But you know, we've got to make the room pretty. Yeah? So that window is costing a lot of money. Depends on the area across which heat is flowing. Okay? And look at this. This depends on the temperature difference divided by the thickness of the walls. So for the same temperature difference, if the walls are very thick, then the rate of heat flow will decrease. Okay? All right, so how does heat flow in solids? In solids, by a conduction, okay, this end is hotter than this end. These guys are vibrating with greater amplitude. But they're not going anywhere, these atoms. They transfer some of their energy by bumping into the neighbors, and then this guy will transfer some of the energy by bumping into him, and eventually heat gets there. When does this process stop? When they're all vibrating with the same amplitude, when the temperature is the same all across. Okay, so heat, when this end of the table is hotter than that end, heat will flow from here to there, and heat flow will stop when the entire table gets to the same temperature. Okay, so this is thermal conductivity. By the way, this is the rate of change of temperature, so the derivative of the temperature with respect to position. Okay. And in this formula, you have a negative sign because heat is flowing in the direction of decreasing temperature, where this is negative, so negative or negative, that makes it positive. Okay. So this is a 100-watt device. Okay. That is 100 joules of heat is being produced on that chip per second. Okay. All the electrical energy is being converted to heat after it does its job. Okay. Now, if you didn't remove that heat, that chip would get too warm and then it would stop functioning. So you have to continuously remove heat. And so you have this metal piece sitting on the chip and which has fins, and you pass air through it. So heat flows from the chip to there, and then you dump the heat into the atmosphere. Okay. So all that heat from your computers is being dumped into this air. And if you shut off the air conditioning, the air would get warm. The supercomputer, so server farms with 10,000 CPUs have a power consumption of 1 megawatt. That's 1,000 homes. Okay. Did you go to the UF supercomputer? Okay. Who went in this room? You did. Okay. So the UF supercomputer room is about half this floor. And it uses 3 megawatts of power. That's 3,000 homes. So the heat produced on 3,000 homes is in half this room. That air conditioning system better not go down. Okay? Because all your bank balances will be wiped out soon as those computers go down. Yeah. And so now you know why all banks have to have backups. You spend millions of dollars on your computer system, and then you have to have an exactly similar backup in some other location. Okay, convective heating. So here's how you warm up a room. There's a space heater. It warms up the air around it. This air rises, gets replaced by cold air, which gets warmed, and eventually the entire room is warmed up. Okay. To keep you warm here, you got to warm up all the air, and a lot of the warm air is up there. Very, very inefficient. Okay. We can't give you a formula for this. Okay. So liquids. So in a solid, here was the difference. In a solid, heat transfer happened without the atoms leaving their location. In a liquid, heat transfer happens where the liquid molecules move. So that's convective heat transfer. Okay? So here's the oceans move an enormous amount of heat. The waters near the equator get warmed up more. And so here's the Gulf Stream that flows like that. Okay. So, and so this stream is about 100 kilometers wide and a kilometer deep. So it's like a river of warm water flowing like that, 100 kilometers wide as the width of Florida, and 1 kilometer deep. And from here to the Embry-Riddle campus. So imagine a river as wide as Florida and 1 kilometer deep. That's flowing like that. And it flows about 5 miles an hour. So this is how this ocean current was discovered. Ponce de Leon, he was sailing in this direction. He had favorable winds and he wasn't going anywhere. That's when he realized that he was sailing in a river that's flowing in the opposite direction. That's how come these currents were discovered. Okay. So here's the Gulf Stream, which is small, and and this convective heat transfer, it takes nutrients and warmth around the ocean. Okay, well, nutrients, which is again important, okay, for life. What emits electromagnetic radiation? Everything. Okay. And so, how much energy is emitted per second? That's the power. Depends on the emissivity. It depends on a property of the surface. Okay. And this is a universal constant. That's the same for everything. It's the same for the wall, for you, and so on. That's the area of the object emitting radiation, and that's the temperature of the object, and that's in kelvins. Okay, so that's in, okay, so if you double the temperature, 2 to the power of 4 is 16. The amount of energy you radiate will increase by a factor of 16. Okay? What this tells you is the net amount of heat radiated. This is your temperature, and that's your surrounding temperature. So right now, because the walls are at a lower temperature, you're losing energy via electromagnetic radiation, and that's the difference. Okay. This is called the Stefan Boltzmann's constant. All right, so here is a, see this, like we said, you're radiating everything you radiate, but you radiate in the infrared region. That's based on your body temperature. Okay. You're radiating infrared, so an infrared radiation doesn't get through this plastic, and so you take a picture, well, with a visible light camera, and of course you can't see that. But you take a picture with an infrared camera that's sensitive to infrared radiation, and now you can see your arm. Something that is a good absorber, is also a good emitter. Also, so an object is called a black body if it absorbs all of the radiation falling on it. By the way, so how do you see this red color? So there's,
The paper's absorbing everything except for the red.
right, okay. So plants are green, so plants don't absorb green. So you want to kill a plant, what do? You take sunlight and put a green filter. You only let green light shine on the plant. Okay? And it can't absorb it. Okay? So if some object absorbs all the radiation falling on it, then it'll appear black. Okay? Okay, so a good absorber, so this is absorbing all the radiation falling on it, is also a good emitter. So when you heat it, it emits in all wavelengths. This is absorbing all wavelengths. So in winter, you want to wear dark clothing, so it absorbs all the radiation. A white piece of cloth reflects all radiation. Okay, so that's why it appears white. It's not a good absorber. All right, I'll just talk about this briefly, and then we'll pause, and then we'll start problems, okay? Well, do you guys want to hear about this? Okay, just 2 seconds. What is this guy?
An atom.
Is a hydrogen atom. Do you know how much energy you need to strip the hydrogen atom of its electron? That's the ionization energy of hydrogen. It's 13.6 electron volts. Okay, that's the ionization energy. So if you shine a photon of 13.6 electron volt, that you can ionize this hydrogen. If the photon energy was higher, it'll strip it, ionize it as well. Okay. So when the universe first formed, it's expanding. There's all kinds of particles. Okay. So this is less than. So the age of the universe is less than 380,000 years. Okay? And the universe is expanding, and the average energy of all these particles are the same. So when the universe is younger than that, the energy of these photons, the average energy of these photons, is greater than 20 electron volts. Okay. And as the universe expands, the wavelength stretches, its energy decreases, the energy of the photon decreases. Okay. So as the universe is expanding, everything is cooling down, the average energy of each particle is decreasing. But when the average energy of the photon is 20 electron volts, let's say, at a younger age, the energy is higher. What will happen? What cannot happen? The hydrogen atom cannot form. Do you guys understand that? Because why can't it form? Because these guys will knock off the electron. So when will the hydrogen atom form? You should be able to answer this.
Cools down,
To what point?
13.6 electron volts.
Very good. The average energy of the photon has to become less than 13.6 electron. That happens at that age. And so now at 380,000 years after the Big Bang, now the photon energy has become such that it's less than the ionization energy of the hydrogen atom, and suddenly hydrogen atoms have formed, and these guys are not talking to anybody. They're not being absorbed. So the universe has become transparent to electromagnetic radiation. And then the universe is expanding. These photons are getting colder. Okay? And so, the temperature of the universe back then was 3,000 degree Kelvin. The universe is expanded now, currently by a factor of 1,000. It's increased by a factor of 1,000. And the temperature of the photons that was 300 degree Kelvin has become 3 degree Kelvin. Okay. So all these photons are running around. The universe is bathed in it, and that is what you're seeing. That's what this is, a map. So you look in any direction, and the photons that are coming at you are at 3 degree Kelvin. Okay. That's the cosmic microwave background radiation. And this map was important because what this is telling you is you're looking at that part of the sky, and these photons have a temperature slightly less than 3 degree Kelvin. Okay. See, the temperature variation is 200 microkelvin. Why is that important? Because that's where the galaxies form. The matter density is higher there, galaxies form there. If the temperature was even everywhere, then you would have no galaxy formation. Yeah, so that's why this is important. All right, we will